Hello everyone, and welcome to Sky Scholar, the channel where you can learn about new concepts in physics and astronomy. I am your host, Dr. Robitaille. Today, I want to present some of the most easily understood proofs that the Sun has a real surface. If you wish to learn more, this paper and the references which it contains should be useful. In the standard model of the Sun, we are told that the solar surface is but an optical illusion, and what we perceive is the effect of rapidly changing opacity at the level of the photosphere. Opacity represents the ability to absorb, reflect, or scatter light. The problem is that the evidence for a solar surface does not occur solely in one range of the electromagnetic spectrum. The Sun manifests its surface at every frequency, from extremely low frequencies sampled in helioseismology to X-ray and even gamma rays. All of these phenomena cannot be illusions. An even bigger problem for the modern solar theory is that the solar structures behave as condensed matter. But for now, suffice it to say that the Sun has a real surface, and as a result, the standard solar model cannot be valid. Let's start with the first example of the Sun's true surface. Here it is, a series of Doppler images taken with the Michelson Doppler imager, an instrument aboard the SOHO satellite. In this series of images, SOHO sampled the surface of the Sun while a flare was erupting. White pixels indicate motion towards the satellite, while dark pixels reflect motions away from it. What we are witnessing is a group of symmetrically expanding rings as the flare moves towards the detector. These rings appear to represent transverse surface waves, exactly like a rock thrown onto the surface of a pond would produce. In fact, the authors wrote, "We have also detected flare ripples, circular wave packets propagating from the flare and resembling ripples from a pebble thrown into a pond." This is important because transverse waves, such as present when ripples travel on a pond, are a property of condensed matter, not of gases. In a transverse wave, the direction of energy propagation and molecular motion are perpendicular to one another. That is to say, ripples move up and down on the surface while the energy travels along it. In a longitudinal wave, energy propagation is in the same direction as atomic or molecular motion. Gases, like the proposed Sun, can only sustain longitudinal waves, and that is why the authors of this study do not discuss surface waves or L waves, which are transverse in nature. They suggest that the ripples on the surface of the Sun are P waves, acoustic or longitudinal waves, acting to buckle the solar surface. The problem with this idea is that the photosphere, in the standard solar model, is said to have a density of only 10 to the minus 7 grams per centimeter cubed. That is a density of a vacuum, and no one on Earth has ever observed P-wave phenomena in a vacuum. Those claims are simply unreasonable. We captured this video as a reminder of what happens to water when a rock is thrown into a pond. In this video clip, the expanding surface wave reminds us of the Sun, and these waves can only be supported by condensed matter. Pure transverse waves do not occur in water as they are mixed with longitudinal components, but still we get the idea that these waves are surface-related phenomena. Some may attempt to account for the ripples on a gaseous Sun by trying to invoke the effect of magnetic fields on a plasma, but the magnetic fields in the Sun are just too chaotic to be able to sustain this symmetric pattern. Furthermore, if the Sun was truly a gaseous plasma, then the only wave that it could sustain would be longitudinal in nature, without surface effects. Much like sound waves traveling to your ear, that is because the Sun does not possess a uniform magnetic field. It is important to note that the expanding rings in these images are increasing from a velocity of about 22,000 miles per hour to 250,000 miles per hour before fading. These observations are telling us something about the structure of the solar surface. It is possible that as the wavefront travels, its energy becomes confined to shallower and shallower regions of the solar surface. This might be providing evidence that the material which makes up the Sun's surface has a layered structure. In water, expanding rings do not increase their velocity as they travel. The presence of transverse waves on the Sun represents one of the simplest signs that the Sun is condensed matter. Even if it were to be argued that we are seeing P waves traveling along the surface, and that such waves are longitudinal, those P wave distortions still require a real surface, and none is present in a gaseous Sun. What is clear is that the optical illusion of the standard model is now behaving like a real surface. It is also said by the SOHO team that the Michelson Doppler imager on the satellite is indirectly sampling the presence of acoustic gravity waves trapped below the photosphere of the Sun. But acoustic gravity waves cannot propagate in a vacuum like in a gaseous solar model. As such, our ability to even detect them indicates that the photosphere cannot have a density as proposed by the standard model. The fact that helioseismic studies can be performed on the Sun testifies that the surface of the Sun is not gaseous, but indeed condensed matter. It is ringing like a bell. We see proofs in the images such as this one, where scientists are displaying the modes of oscillation detected on the surface of the Sun. These oscillations represent extremely low frequencies, as the vertical scale in the image is in millihertz. Helioseismologists seem to forget that seismology is a science of condensed matter. Now let's look at a few video clips of coronal mass ejections. The first clip shows two separate ones. Notice how material is being almost pulled off the surface of the Sun. Such films are highly suggestive that the outer portion of the Sun is organized in layers. Now let's examine this second clip. Look what happens when material falls back onto the surface of the Sun after a coronal mass ejection. Do you notice how the surface is being brightened at the point of impact? If the photosphere was a sparse gas with the density of a vacuum on Earth, why would we observe any impact when material falls back onto the Sun? Again, it is because the solar surface is real and not an optical illusion. Now we can examine this movie showing granules on the surface of the Sun. In the context of the standard solar model, granules are said to be the result of uprising convection currents. In modeling these currents, solar physicists often invoke analogies to Baynard convection on Earth. However, Baynard convection, by definition, is a surface-driven process. Furthermore, careful mathematical analysis of granules demonstrates that these objects follow the laws of space filling for 2D structures, something which is impossible for gases. More details relative to this finding can be found in this paper. Next, let's take a look at this video clip of the Sun. It is an X-ray presentation taken at 94 angstroms by the NASA SOHO satellite. Notice in this video that the X-ray intensity is much brighter at the edge or limb of the Sun than at the disk. What is happening here? If you examine this figure, you will begin to understand. When we observe X-ray lines on the Sun, by examining the center of the disk, we find that the lines have a certain intensity. However, as we move to the limb, the intensity begins to increase very slightly because we are now sampling a little more of the solar atmosphere. Notice, for instance, that the path length of line 1 and 2 through a hypothetical solar atmosphere. The path length of line 2 is slightly longer than the path length of line 1. Hence, we are sampling more atmosphere in line 2 than line 1, and that's why the intensity of the X-ray increases slightly. However, as soon as we cross the solar limb, as reflected in line 3, the X-ray intensity doubles because now we are effectively sampling twice as much of the solar atmosphere. Because of this differentiation between the atmosphere and the solar surface, the Sun is telling us, I have a real surface in the X-ray range. Finally, let us examine the Sun in gamma rays. Powerful flares are known to produce high-energy gamma rays which are visible near the solar limb. The effect is particularly pronounced when the gamma rays have energies greater than 10 mega-electron volts. Very few, if any, such rays are ever emitted at the center of the solar disk during a flare event. Now, how can something be visible only when it occurs at the limb of the sun? But it is not visible when it occurs at the center. In the end, this can only be a question of viewing angle. If high-energy gamma rays were being produced in all directions equally, then viewing angle would not be important. But what we are actually seeing is an effect of having a true surface. The flare is revealing a geometrical reality at the point of emission. There is a three-dimensional setting involved, and that is why the flare appears the way it does in producing gamma rays. We are witnessing what is referred to in science as an anisotropic effect. The geometrical conditions are not the same in all directions, and as a result, the authors of the paper describe the effect as strongly anisotropic. Anisotropy refers to the difference in a material property as a function of direction along x, y, or z. Crystals, for instance, often display anisotropy in their structure. High-energy flares produce their powerful gamma rays in a manner that these end up being emitted nearly tangentially to the solar surface, as shown in this little figure. You will notice that as the flare crosses the solar surface, gamma rays are almost perpendicular to the flare direction. Any gamma ray produced when the flare is on the limb therefore has a chance of being viewed from Earth. You can think of these as emitting in a cone-like fashion near the surface, at the base of the flare. If the flare occurs at the center of the disk, any rays emitted from the cone move away from the detector on Earth and therefore cannot be detected. As such, high-energy flares seem to produce gamma rays only when they are at the limb of the sun. This is simply a question of being able to detect the rays from our position. In order to account for the production of these gamma rays, solar physicists invoke magnetic mirroring of electrons, which descend upon the photosphere from the corona and thereby provide the needed energy. They place the required hypothetical mirror near the level of the photosphere. In this way, they once again create an imaginary surface instead of insisting that a real one is actually present. But the most important conclusion from such observation is that flare production is demonstrating an interaction with a real surface, not an imaginary one. It is not necessary to bring energy from the corona, as a solar surface contains more than enough energy given its powerful convection currents. In this respect, note that atoms which make up the flare are traveling perpendicular to the solar surface, but the surface also has differential motion, as seen in this figure. As such, while the flare is occurring, surface atoms are colliding with flare atoms. This is because their direction of motions is perpendicular to one another. The energy dissipated in the flare are manifestations of these powerful collisions, which are revealing that the solar surface is concealing tremendous energy in its convection currents. There is plenty of evidence that the sun has a real surface. This video focused on proofs which are easiest to understand. But I have not presented the most important scientific proof, the production of the solar spectrum. I will discuss the solar spectrum in future videos. For the time being, I would like to say that at every frequency which can be considered, from ultra-low frequency oscillations of the solar photosphere in the millihertz range, to collisional results, to optical visualizations, to X-rays and gamma rays, the sun has provided us with ample evidence that it has a real surface. In fact, through its coronal mass ejection, the sun is even hinting that the material at the level of the photosphere might be layered. The increasing velocity of the expanding rings produced by a solar flare suggests the same. We will discover more evidence that the sun has a real surface in future videos. I hope that you like this short exposition relative to the true surface of the sun, and will join me as we look more closely at the sun, the stars, and beyond. If you enjoyed this video, please leave a like. In addition, subscribe if you want to journey with me through space here at Sky Scholar. Comments are always welcome down below. I'll see you soon on our next video.